Good morning. Damn, no one's here. Good morning. Thank you. Thank you. You know, God, it's already 9:30. I've already been up for 5 hours, so I don't know why anyone else is asleep today. This is the spring working group meeting. This is IETF 119. We're in Brisbane, in Australia. We have a lot of people remote as well. So we're going to start. I am Alvaro, and Bruno, who's one of the other chairs, is online. He's back home in France. I believe Joel won't be able to make it today. Bruno, do you want to say hello?
Hello, good morning.
Everyone says good morning, even though you couldn't hear them, or I couldn't hear them, but you know. Okay, so why don't we start with the slides? Let's go to the next one, Bruno. This is the note. Well, important things about this is not just IPR, but it talks about behavior and how we want respect in the meetings, how we want to treat everyone else as participants. So please, if you haven't read it, actually read it, and you can visit the BCPs down at the bottom. Next slide. Some general meeting tips about your participation, whether you're here in person or remote. Please make sure if you're here to scan the QR code. That will also let you get in the queue if you want to say something. Next slide. We are taking minutes. Shuping, who's our secretary, is taking the minutes in that link over there, but we would benefit very much from your collaboration. Please help with the notes, especially if you make comments. Please take a look that we captured the right thing, captured your name correctly. The link again is right there. The next slide. So we have the compressed SRB67 list encoding document in Working Group Last Call. This was initiated back in January. There are, according to our notes, a couple of open points. We're going to have a discussion later today on that, where Francois is going to present the status of where they are addressing especially the bigger issues. The one that is the bigger one is, of course, the upper layer checksum that has been discussed on the list. So we'll look forward to that discussion. Next slide. We did manage to publish 2 new RFCs. Thank you to our AD, Jim, who did a bunch of the heavy lifting. We have 2 new RFCs. We know that there are a bunch of documents in the queue. You can visit the wiki, the Spring Wiki, to look at the queue on adoptions and working with less calls. We're working on trying to move that along. Next slide. We have a full agenda, as we always do. As you can see, the first couple of topics here have a little bit more time because we expect there to be a little bit more discussion there. We will prioritize those over anything else. So we want to talk about these and take advantage of the time that we're together in person, including, of course, the people online, to discuss the issues in a high bandwidth conversation. There are, as you can see at the end, we listed some work if time permits. We hope to at least finish the ones that are above that. But again, we're going to give priority to the first couple of drafts in there. Next slide.
Finished.
Nope, that's it. So, okay, great. So unless anyone has any comments bashing to the agenda that you want to add or delete anything. Nope. Okay, so we're going to go to the first one. Francois, I believe, is online. So Francois, you can go ahead.
Okay, thanks, and good morning, everyone. So I'm going to present an update on the compressed zip draft today on behalf of my co-authors. Next slide, please. Thank you. So first, a short status update. What have we done since the last presentation in Prague? First, we addressed the remaining comments from the reviews of Adrian and Boris. That was in revision 10, so in December. Following that, the working group closed the issue number 1, which was the clarity on one or multiple data plane solutions. So we did that in mid-January, and that was the last remaining issue that was tracked on the GitHub. Then we, as Alvaro already mentioned, the working group started by the end of January. We got a shepherd, so many thanks to him. We've also got a lot of support during that working group last fall. So many thanks to everyone who supported that document to move forward. Aside from that, we've received a few comments. In particular, we've got comment from Martin and Dhruv, which we addressed in revision 12 of the document, and we'll come back to that in a minute. And there is one outstanding comment from Andrew, and that is the one on the L4 checksum. We'll also come back to that in a couple of slides. Finally, we've got a review from Alvaro on behalf of the sprinters. So thanks a lot, Alvaro, for spending the time and effort to look at that draft and produce such a thorough review. That's very much appreciated. We've tentatively addressed this review in the revision 13 and revision 14. So revision 14 was submitted just a couple of days ago. If people have not yet had a chance to look at it, please do so. Next slide, please. Okay, so now the main changes since revision 9, which was the last one that we presented. First, in section 4, we've added some operational guideline on the selection of the CSID flavor, following comment from Dhruv and also from Alvaro. So obviously the draft is not intended as a deployment guide, but it was indeed important to highlight the key aspect to look at when an operator is evaluating which flavor to deploy. So aside from that, we've also clarified in the same section, really separated the implementation requirement from the operational guidance when it comes to locator block and CSID length selection. So for each flavor, there is no one length that must be implemented, and that is meant to serve as a baseline for interrupt. And aside from that, implementers can support any other length if they want to. There is no restriction there. And the rest of this paragraph are just operational guidance. But hopefully this is more clear now. And next slide, please. So then in section 6, we've had a comment from Martin about the SID structure validation and what to do when the segment routing source node receives a SID with a missing or an invalid SID structure. So we've clarified in the revision 12 that those SIDs would be incompressible, but they are not invalid, they are simply incompressible. And then also in that section, following a comment from Tal, we've added in revision 10 a new subsection on the upper layer header checksum. So that new text is basically paraphrasing what RFC 8200 is saying, and basically that is that we should use the destination address as it is supposed to be received by the final destination when computing the checksum. Next slide, please. Then in section 7, we reworked that to align it with the rest of the document. In section 12, which is the security consideration section, we've expanded it because the previous version was very short. So we've expanded it to explain how the compressed SID fits within the security model that's defined in RFC 8402, 8754, and 8986. And finally, we've removed the open issue section in the appendix because all of the issues that were tracked there were closed. And we've added the full pseudocode for all the seeds in this document. Before that, we only had the full pseudocode for a couple of seeds. We've added it for the remaining ones. Next slide, please. Okay, so now we are getting to the remaining open issue, which is the L4 checksum verification that was raised by Andrew. We've got over 30 emails on that topic on the mailing list, so that's well, pretty big. I try to extract the most important points that were made during that discussion and put them on this slide. And the chairs have asked us to continue the discussion during this meeting. So first, let me summarize the point of view of the authors on that topic. And I'll start with what is not a problem. So any checksum validation at the destination, at the final destination of the packet will work. That's not a problem. In addition to that, any middle box that does not attempt to validate the L4 checksum will also work. So that's obvious. But judging from the email discussion, it seems that the L4 checksum verification is not really a common capability on those middle boxes. So it felt important to mention it. So now, what is the problem? So again, from the point of view of the authors, the problem is middle boxes attempting in-flight checksum verification of non-encapsulated source-routed IPv6 packet. That's pretty specific, but it's actually a specific issue. I would also add that the problem is not really specific to compressed seed, or not even specific to SRv6 at all. In fact, there was an email, I think, from Ron Bonica in that thread saying that he had to address that very same issue in the CRH draft in 6.1. So now we're getting to the discussion part. And I think as an author, the main question that I would like the working group to answer is that problem something that we want this document to solve or not?
So I see no one running to the queue. Okay, Andrew entered, but before I go to Andrew, I think I want to word the question a little bit differently. Not only is this something that we want to solve, but something that we need to at least address. And by that, what I mean is, do we need to at least raise awareness of the issue and the possibility that some things may not work? Having said that, let's go to the queue. So, Andrew.
Hi, firstly, Andrew from Liquid. Good morning, everybody. It's 2:30 in the morning here, so excuse me if I'm a bit fuzzy. I would say that, yes, to me, this is an issue for various reasons. I'll be responding to that more on the mailing list. But I think my question on this one's more to the chairs. We acknowledge in here that the L4 checksum does have a problem on middle boxes, and that potentially runs into conflict with 8200. Therefore, I would ask that at minimum, this is last called and made aware of in 6-man, where 6-man as the holders of 8200. And I'd like to know from the chairs if they do plan to do that. And potentially either update 8200, though I don't know that that would be an acceptable solution, or we biz 8200 to fix this.
I'm just going to continue with the queue, but I know for a fact that, of course, 6 is aware of this. There's a lot of cross-pollination of participants, and I know the chairs are also aware of these issues. My personal opinion is that we don't need to update 8200. We need to make indicate in the draft and make put awareness on the fact that there are issues with middle boxes, and then let whoever is going to deploy this make their decisions. Suresh, you're next.
Thanks, Alvaro. So I kind of agree partly with Andrew, but like mostly with you, right? Like I don't think it requires a 8200 update. So the general dilemma I have is like the middle box is doing something wrong, right? Like the middle box is not supposed to verify the L4 checksum. So I really think like us trying to like bend over backwards to fix it is like a bad idea. But I do understand Andrew's concern, and I really think we should document something saying like, hey, this is not going to work. So like, this is like, if this is something you need in your network, you should like be cautious about that. It's like probably where we should go. But like, and I'm fine with like, kind of talking to 6man. If like, if you want to do a formal thing, I think that's good as well. But personally, I think the middle boxes are doing a layer violation. Let's not kind of legitimize them by doing protocol changes to kind of accommodate them what they shouldn't be doing.
Anyone else? Okay, so what I'm hearing, at least from this brief conversation, is that we want to bring awareness of the fact that there are scenarios where this might not work, and what are the cases for that, and then let the user, the operators, whoever deploys this, to figure out what they want to do. So apart from the outstanding reviews, I think this, of course, is going to need another revision of the draft, and we'll take some of the discussion back to the list. Thank you. Okay, so now we're going to move to the next presentation, which is the security considerations work. Before I move to that, I want to say two things. Sorry, Luis. One is, I was reminded by Drew that there is going to be an SRv6 operations BOF on Friday at 9:30 in the morning, and I believe it's going to be upstairs in the big room. So if you want to go, please go. I would imagine this is of interest to everyone here since we work on segment routing. Again, it's a BOF. So, and since we just talked about maybe operational issues, then it would be a good thing to be there and see what the proposals are. Now, going to the security document, if you remember, this is a request that we got from the IESG to have Spring address more thoroughly look at the security considerations of SRv6. So we assembled a team, and the team has been working on that. And so Luis is going to update us on that.
Thank you, Alvaro. Hello, everybody. This is Luis Contreras from Telefónica. I will present the operational security considerations on behalf of my co-authors, Nick, Tal, and Tian. Next, please. So the goals and objectives of the document is basically providing a comprehensive view of the security threats in SRv6. So in such a way that we can identify beforehand the potential risk and also mitigation actions for them. The idea is to approach the problem from an operational perspective so that this document could be useful for operators of the networks. So in such a way that we can identify beforehand the risks and the operational gaps that probably could be also worked out in here later on. Next, please. So where we are, there was an initial version that was presented in Prague in the previous IETF in 118. We have released version 01 for this meeting, and we have somehow restructured a little bit the document trying to put the contents in a much more clear way. things that we have been working on, we have worked on technical details. I will comment in the subsequent slides. We also added a little bit more of terminology in order to clarify the terms. Some of the open points were moved to a specific section that somehow we can register there and list them, what could be the potential new topics to address in the forthcoming versions. I was also part of the draft as well for this new version. Next, please. So going into the technical details, what is new now? We added a new section on attacks. This was a reformulation of a previous chapter on security considerations, and essentially we somehow structured in a different way, trying to describe the problem from having an overview of the problem, then the scope, and then the impact. So we think that this is a clear way of defining the problems, or also facilitates the fact of identifying if something is missing. So because we will encourage later on contributions, so probably in this way it's easier to identify something we are missing some parts. Attacks considered so far, we describe the segment routing modification attack, the reconnaissance of the information flowing because someone external could observe the packets, the problem of packet insertion, the also potential control and management plane attacks. So that we could have these issues, this risk also from the control elements, the controllers, and some other problems like spoofing and so that somehow could be general, not only general to segment routing, but also coming from the fact that we are leveraging on IPv6. Next, please. We also expanded a bit the section on mitigation methods. The idea here is to describe potential mechanisms for mitigate the previous attacks that I commented before. And by now we are considering two methods, the filtering that could be applied for both the segment routing header and also the address range that is used in the packets, and also the encapsulation of packets. Next, please. And then also we have started to describe implications in existing networks, in existing equipment in the network. So there was a previous subsection that we have moved to the category of main section in the document, so impacting the problems in existing equipment. The implications considered so far are limitations on filtering capabilities and also middle box filtering issues. We also certainly we didn't elaborate it. The third one, which is emerging technology growing pains, is a kind of placeholder for new content. By now it's simply stated and that's all. So a part of all of this technical progress in the new version, also let me just remind that there is also a section that was in the previous section about the threat model that we are considering in the document. So somehow also serves a kind of guidance of what you can find in the document in terms of threats analyzed. Next, please. So more details about the document. The document is in a public repo that is maintained by Nick. So we encourage all of you to go through that and propose changes and any pull requests for the parts that you consider necessary to fix and to amend. Reviews are more than welcome for sure. And basically this is available for all of you. So we encourage your participation on this. Next, please. So as next steps, we think that the document is ready for working group adoption. So to transfer, let's say, the ownership to the working group for progress in the document. As said, we would like to collect more comments, more feedback from the working group. Probably we are missing things, so clearly with the contribution of the working group, we will improve the document. And something that is yet pending from our side, and one of the next steps that we are considering and that we didn't yet go through, is to survey somehow the existing security considerations across the working group documents and all existing RFCs. So we think that it could be convenient also to have a look to what is already there, and also document maybe a kind of annex or something like that, so providing a survey of what is also in some other documents on SRv6. And I think that that's all.
Thank you, Luis. So how many people have actually read this draft? Okay, a handful. Okay, so just a quick informal poll. How many of you think we should adopt this document into the working group? You can raise your hand even if you didn't read the document. Okay, do any of you, Tom, go ahead.
I had a particular problem. It's Tom Hill from BT. So at the moment, the gap analysis section is very, very short. And I wondered whether or not it would be prudent to work on that some more before beginning adoption. So there's at least a starter for 10 in there for something to actually suggest that we work on.
So I think maybe, well, I'm not sure if the answer is only me from the chairs. Maybe, yeah. For we have clear the document is not definitive, so we need to work more on that. And
no, but I mean it's like a paragraph. It just says this section will be a gap analysis. So I think there could be a little bit more work that goes into that particular point, that section, before and from that I would, otherwise, yes, I would be happy to start adoption and support an adoption call, but that section is very, very slim.
Okay, yeah,
non-existent technically.
Point got it.
And just a quick reminder, adoption only means that the working group is interested in this work. It means that we hope the working group, everyone in the working group contributes to it, and it doesn't mean that we will end up publishing it, right? Not just for this document, but for everything else. In this case, of course, the A is yes, so we have to publish something at some point. Darren.
Yeah, Darren Dukes. Hey, first, thanks for the update. It's I think it's improved a lot format-wise from the first revision that you guys had produced. I like your final point here, work on surveying existing security considerations across working group documents and RFCs. That, of course, needs to include RFC 8754. And my read of the document at the moment is that it doesn't cover what was considered in the security analysis of RFC 8754, nor the mitigations that were considered in RFC 8754. In fact, it's missing some important ones and have some that were discounted because they're not useful. So that last bullet point is going to be particularly interesting. And I'd like to see probably some more individual work go into this to find out if we can differentiate and maybe expand on those considerations and get something more than what's currently documented.
Yeah.
Okay.
Thank you.
And since you're here, yeah, hopefully we can talk this week.
Thank you. We took the decision for starting somehow from scratch and later on coming back to what is out there. So now is the point of coming to that point.
And that makes perfect sense. Appreciate it.
Thank you.
Okay, so I think what we're going to do is, of course, we're going to take this to the list and figure out there what we're going to do with this document. Just a quick reminder, this document, we selected a group of authors. This is not a design team, right? This is just a group of authors, just like any other document is going to go through the normal procedure of adoption and everything else. At some point, if it is adopted, we will move it to the Springs GitHub space. It is great that we can go and do pull requests and other comments and stuff there, and discuss issues. Please do so also on the mailing list, because the mailing list is still the source of truth, right? So let's please don't forget that. Thank you.
Thank you.
So we're now going to go to the microtap segment. And this is going to be a remote presentation. Gunwinder, I don't know if you're saying your name remotely correctly.
That's fine. Thank
There
you.
we go.
Okay, so hello everyone. This is Gurminderjeet Bajwa from TELUS. I'll be presenting on microtap segment on behalf of the co-authors. Next slide, please. So what's the intention of this draft? It defines a new segment called the microtap segment, which is used for capturing traffic of interest from the transit routers, also known as P routers or LSRs, for performance or packet analysis. The instruction that microtap segment represents is replicate the packet and send the copy to a destination. How do we use microtap segments? So one or more microtap SIDs are strategically placed in the SID list, which results in traffic tapping at targeted points within the network. A router encountering the microtap SID makes a copy of the packet and send it to the router connected to a monitoring tool. And the original packet continues on to its destination. The example on the next slide will provide further clarity to the concept. Next slide, please. Okay, so in this example, we have a small service provider network comprising of router A, router B, C, and D, which are running SRMPLS. So let's say client A sends traffic to server B on the other side through the network. So the path is client A, router B, router C, router D, and server B, right? So we would like to capture the traffic at router B for packet analysis, let's assume, right? So on router A, microtap SID is placed after router B's node SID in the SID list. Also, router A classifies the traffic of interest with 5 tuples or any other method and pushes that SID list to the packets. When microtap SID becomes active, which would be on router B, it basically replicates the packet and send the copy to a remote monitor. And how does it send the packet copy to remote monitor? The answer is by imposing router B's node SID. Now, what happens to the original packet? The router B pops the microtap SID of the original packet and continues forwarding it to router C. Going back to the replicated packet, when microtap SID becomes active on router D, it sends the packet to monitoring tool connected to it. So in this example, the routers are running SRMPLS. However, a high-level concept also applies to SRv6-based network. Next slide, please. I won't go into details around control plane signaling for different protocols, but yeah, I'll let you read the draft for that. But a couple of things that I would like to highlight here is, so from signaling perspective, we need a couple of things. So each node that supports microtap function will advertise its capability to other nodes in the network and also PCE. For SRMPLS, this draft defines a new flag T in the flags field of prefix or adjacency SID TLV or sub-TLV for the relevant protocols, which basically indicates that a microtap SID can follow the given SID in the SID list of a packet. Similarly, for SRv6, microtap node uses a new flag T in the flags field of SRv6 capabilities sub-TLV to indicate that a microtap SID is allowed to follow the prefix or adjacency SID in the packet. The second thing we need is that each node that connects to a monitoring tool advertises the microtap SID to other nodes in the network and PCE. For SRMPLS, this draft defines a new microtap SID TLV or sub-TLV for the relevant protocols for advertising the SID. The newly defined microtap SID TLV or sub-TLV, it basically mimics the format of prefix SID TLV or sub-TLV. So and for the for SRv6, microtap function is advertised by microtap SID is advertised by the monitoring node within SRv6 and SID TLV that's associated with SRv6 locator TLV. So we are not reinventing the wheel here. In fact, we are using the knobs that we have at our disposal. Next slide, please. So this technique of capturing the traffic from a transit router provides a number of benefits compared to the existing methods like remote mirroring. With remote mirroring, we would capture traffic based upon the incoming port or SID, which captures a large volume of traffic, right? So you would use a lot of replication resources on your transit router. And not just that, you will also have to backhaul that large volume of traffic to your tool farm, which would consume a lot of bandwidth in the network. And moreover, you would need a packet broker, which would filter the traffic and send only the traffic of interest to the monitoring tools. With MicroTap, you can be very granular and only capture the traffic of interest on your P routers. So there is a bandwidth saving, no need for packet brokers, no excessive use of packet replication resources, which are also used for multicast and MVPN-based services. MicroTap segment uses segment routing, a standard technology to tunnel the replicated traffic to the monitoring farm, whereas in a remote span or mirroring, different vendors use different tunnel technologies in their implementation, which sometimes cause or usually cause interoperability issues. Another advantage or another benefit is that MicroTap segment doesn't require any configuration on your transit router, which basically adheres to the idea of keeping the LSR low touch due to its blast radius, right? And last but not least, this new technique is less resource intensive. What that means is that your transit routers, they do not need to look deep into the packet to be able to figure out whether it needs to replicate it or not. Next slide, please. So what are the next steps? So we would like to complete the draft. There are some missing sections, a security section and other missing details. And your comments, questions, and input is most welcome. It would help us refine the draft.
Okay, we have a couple of people in the queue. Greg.
Hello, Greg Mirsky, Ericsson. Thank you for presentation. I have two questions. One is, have you compared this mechanism that you propose to in situ OEM loopback functionality?
We have not. So if you can provide a bit more details, then yeah, we can do that and answer any questions you may have.
Yes, and the second is, so do you think that this micro tapping will need to be rate controlled as a security measure?
Yeah, so absolutely, and this is one of the advantage of this method of capturing the traffic, right? So as I mentioned, existing methods, you can capture the traffic using remote mirroring or port mirroring today, but the problem with that method is you end up capturing a lot of traffic, right? So with this method, you can basically pick a flow and then use use the newly defined SID list for only that particular flow, right? So basically, you're controlling the volume right at your head end. Does that answer your question?
I'm not sure that existing methods like port mirroring with IPFix really cannot do filtering and send, for example, any nth packet, so thus providing you rate limiting. But let's do it on the list. Thank you.
Yes, yeah. So you're right. So you can basically, enable filtering on your transit routers, but you have to look deep into the packet to be able to, capture the traffic of interest. And when you do that on a transit router, it's hauling a lot of traffic in your network, right? So maybe that's not the preference, right?
Safar, you're next.
Hi, thanks for the presentation. So when we worked on SRv6 ONM RFC 9259, we came across a similar thing that let's do some thing specifics to a SID that can do this replication behavior. But we didn't take that option because that changes the packet itself, which means also it changes the hashing of that packet in the network. And now you're no longer going on the normal traffic path. So as soon as you put something for your tapping, then your behavior is different, your delay may be different, there could be some other implication of that. So your traffic flow is going differently. So the way that it was solved for ONM is to just put O flag, which is completely controllable at midpoint nodes where the end processing happens. And that could be further control on a specific SIDs that are actually data processing SIDs. And they are processed the way the data packets are flowing. There's no specific SID added just to resolve that, just to avoid that problem of tap packet not following the data packet path. So yeah, so I think that's my comment about this, and I'll be happy to hear from you and discuss this.
Yeah, absolutely. Yeah. So yeah, that is, I think it depends upon your use case, right? So when you say not follow the traffic path, you can use other methods to so path tracing as an example, to know the path of your packets, and basically make sure that your the packet that you're fabricating with this technology, it takes the same path, right?
Yeah, but if you look, let's say if you introduce a SID, then the hashing in the network will change. So all of a sudden, the packet that you're sending with tapping would follow a different path in the network.
Okay, but I thought you can control that with the SID list, right? The path of the packet.
So you will always, for a flow that is going, you will always do tapping on that flow, and you will never change tapping. You will never take it off tapping. Anyway, we can take it off. Yeah.
Okay.
But if you introduce on the fly, there's an issue.
Okay.
So we might have to take some of that to the list. I put myself in the queue, and I'm going to actually stand over here. Just so it's clear, I'm not speaking as a chair. I just have a question. So it looks like, if I read this correctly, the microtap SID is originated and announced by the monitoring node, right? Not the node that is actually acting on the SID.
Yeah, that is correct. Yeah, not the node that's tapping the traffic.
Correct, which is different from all the other SIDs that we have, where the node who acts on the SID is the node that advertises the SID. So, I mean, besides that being kind of weird in light of 84, whatever the architecture RC is, I think it opens some other security considerations, right? Where you can advertise SIDs and then just have people tap the traffic and not be there, or cause some congestion issues that I think is what Greg may be thinking about. So just think about that, because it is not the regular behavior. So there are probably other considerations that we need to look at there.
Yeah, let me comment on that. So it'll be similar to a node SID as an example, right? So a node SID, when it hits the transit node, and if it's not the end destination, what it will do is basically swap the SID and send it to the destination, right? But on the destination, the behavior is different, right? It will pop the node SID. So it's the same label, but different behavior on different routers.
Okay, so I close the queue because we need to move on. Thank you for the presentation. We're going to move on to the next presentation. And yeah, there are some open things that we should take back to the list as well.
Okay, sounds good. Thank you.
Not just my question, but other questions that came up here. Thank you so much. Okay, the next presentation is Yixon Liu, who I think is remote as well.
Yes, thank you, Chairs. Can you hear me?
Yes, we can.
Okay, thank you. Uh, I will introduce the flexible candidate path selection of SR policy on behalf of my co-authors. This is the second presentation of this draft. Next slide, please. For the background of that, per the RFC 9256, as we know, as long as there is a valid SL in the active CP, so the CP we think that is valid. But we can add the situation that the parts of the remaining SLs may not meet the forwarding performance requirements, such as the bandwidth or the delay or the packet loss rate. For example, in the slide, sorry, for the CP1, we have 3 SLs, and two of them are in invalid state. So there is only one SL remain. But the actual traffic flow rate is about 120 Mbps. So, but the but the CP can provide only 100 Mbps. But because the CP2 is has a lower preference, and the traffic will not switch from the CP1 to the CP2. So that is a problem. So next slide, please. In this chapter, we provide the flexible candidate path selection mechanism. Firstly, we'll check whether the paths meet the quality requirements. So only the valid paths that meet the forwarding quality requirements that lack the bandwidth delay or packet loss rate can meet these quality requirements can be selected as the active paths. Secondly, if multiple candidate paths meet the quality requirements at the same time, or if all of them not meet the requirements, so we selected the active paths according to the RFC 9260 to 56 section 2.9. So next slide, please. We define some threshold parameters of 2 levels. For the SR level, we define how to measure the jitter and the latency or the packet loss. When these parameters of a valid SL cannot meet the specified threshold requirements, so we regard the SL as an invalid SL, and we will no longer to load share the traffic. And for the CP level, we define the available bandwidth or the actual bandwidth. That means the sum of the pre-config bandwidth or the actual remaining bandwidth of all the valid SLs in the CP if they can meet the threshold requirements for other parameters. Next slide, please. So the selection process. Firstly, we configure the threshold parameters on the CP of the head node. Secondly, the head node will monitor whether the available resources and the forwarding quality of the CP exceed the threshold. That means it cannot can or cannot meet the requirements. Thirdly, when the available resources are less than the threshold or the forwarding quality and cannot meet the threshold requirements, so we will select a new CP. After the old active CP eliminates the failure or improve the forwarding quality, whether to recover can be specified by the configuration. Next slide, please. So this is the example of how to select the best path based on the E2E delay. The requirement is that we need the forwarding parts, the latency must be less than 200 milliseconds. So in the slide, the CP1 and the CP2 only have single SL. If the delay, actual delay, cannot meet the requirements that is 200 milliseconds, actual delay have beyond the 1 second. So it will switch from the CP1 to CP2. And but if there are multiple SLs in the CP1, like SL1 and SL2, if only SL1 beyond the threshold, and it can still the traffic can still use the SL2 to forward the traffic as long as it can meet the other parameter threshold. Next slide, please. So this time we changes the draft to the version 5 according to the comments of last presentation. Firstly, we add the principles of for using the threshold at the SL level and the CP level that had been clarified. And secondly, we add the use case based on the delay. Next slide, please. The next step, we will add some measurement for the parameters we mentioned in the previous slide, and we're seeking for the more feedback from the working group. Thank you. That's all.
Thank you, Yusong. We have Himanshu in the queue.
Himanshu Shah from Siena. I have a clarification question. So basically, SR policy is built based on the intent, right? So all the candidate paths that are there, candidate path 1 and 2 and all that, which maybe the intent may be the lowest delay, you would assume, you would think that you are monitoring all of them and whether a particular candidate path is eligible for and meeting that requirement. Do we really need additional stuff like this to select a specific candidate path? That's the clarification.
Because when we first when we use the CP or the SL, it may be achieve our requirements firstly, but the forwarding quality in the CP or in the SL maybe get worse in the running state. So this draft we want to monitor the state in real time and adjust.
I agree with that. I agree with that intent. But what I'm saying is that is implicit. That is built into this all the candidate paths and monitoring whether they are still observing the intent or not, right? Or meeting your SLA requirement. So it is assumed that you would be doing that. I don't know whether you explicitly need this additional criteria to select a specific candidate path. That's all. I mean, we can discuss this offline on the list or something.
Okay, thank you.
Sure.
Hi, this is Sue Hares, IDR chair. Can you tell me how the adding this will change the amount of data flow that occurs? Will it change the rate of sending in candidate routes? Will it increase it? Will it decrease it? I realize why you might want it, but have you looked at what it does to the flow pattern of the BGP updates?
So sorry, I can't catch your question.
Did my voice not make it? I don't know. Oh, let me try your question. The candidate paths go in through BGP-SR. How, when you add delay and change in like this, how much does it change the rate of things being sent? Does it, when you're adding delay thresholds, are the delay thresholds changing or going back and forth? Is it going to change the pattern? Does it happen once in a great while? I was just trying to look at the data rate on it. And if it doesn't make sense, I won't take any of your time. I'll send it to the list.
Yeah, Yusong, yeah, we're probably going to have to take this to the list. There's actually a very similar question on the chat from Antoine. So yeah, let's take that to the list. Let's move on. Kedden.
Ketan Talaulikar, Cisco. Actually, I wanted to answer Sue's question and also on the chat. I believe this, and I'm not speaking on behalf of the author, but I understand that this is more like a one-time thing where the SLA, like a delay threshold, is sent down with the SR policy. So I do not think it changes the BGP SR policy SAFI updates. But on the other direction, if the thresholds are something that keep changing or flapping, then it does introduce churn in the BGP LS reporting of the SR policy. I don't know if Sue, that answers your question.
Yes, Sue says yes. Thank you. Okay, so there's no one left in the queue. Thank you, Yusong, for the presentation. We're going to move on.
Thank you.
We now have Amal, who is also remote in the next presentation.
Hello,
Go ahead,
good
Amal.
morning, everyone. Hello, good morning, everyone. This is Amal Karboubi, and I will be presenting the seedless optimization for circuit-style SR policies on behalf of the authors. Next slide, please. Yeah, so just a brief refresh about circuit-style SR policies. So these are basically bidirectional co-routed policies which exhibit key characteristic of connection-oriented world or transport-based services. Notably, we're looking for strict bandwidth commitment per path, meaning we need to have bandwidth are reserved on both primary and backup, and traffic is not allowed to go on any link where reservation is not made. We also need to have persistence and deterministic end-to-end TE path that will honor at all time the SLA constraints and delay as prescribed by the user. We need also to have end-to-end protection scheme and restoration mechanism, notably sub 50 millisecond protection switchover, as well as some monitoring and maintaining of a path integrity end-to-end. There is currently an IETF working group that addresses this use case. However, the solution does prescribe that the SID list for such SR policy will need to encode every single hop in the path using only persistence adjacency SIDs. This may lead to a large segment stack that may not be feasible for low-end devices, which we may find in the access network due to limited MSD. Now, we can obviously use binding SID as workaround. However, that also brings an operational cost to the table and some troubleshooting complexity. So our enhancement proposal is to remove the need of fully encoding every single hop in a SID list and allow a SID list optimization. Basically allow usage of node SID or in general non-contiguous SIDs instruction as per the traditional SR architecture. And then the problem we would need to deal with is how to prevent traffic from going into unintended path and their topology changes. Next slide, please. Yeah, so one of the issues of using a compacted or this optimized SID list is a deviation that may occur due to failures. So this is illustrated by this example here. So this is a normal case where the PCE will compute a path for a service according to the current network state and available capacity at that time. This path we will refer to them as intended path. It will then encode this intended path as a set of instruction into the headend using a SID list that may contain node SID or adjacency SIDs as it sees fit. So during steady state, the expansion of such SID list and the intended path are always matching. However, when there is a failure, the expectation is that the headend, it will switch back to the secondary candidate path. However, that will be only momentarily, because once IGP converges, and now each node in the path will regain the shortest path to its next available node SID, the candidate path 1 will become available again and valid for selection, and the headend will switch back to the CP1. Now we get traffic flowing on candidate path 1, which is a post-convergence path, which is not matching our intended path, and this path may actually be not honoring our SLA or going on to links that are where we have not made bandwidth reservations. Next slide, please. So in order to deal with this problem, we have introduced a new flag at the candidate path level that we call eligibility. The role of this flag is to control the candidate path selections. So when ineligible, the candidate paths will not be considered for SR policy candidate path selection. And we rely on the headend router on failures to mark the path as ineligible, and we only rely on the PCE or the owner of the intent to actually restore it back to eligibility. So we will be running connectivity check validation on all the parts of SR policies. We can use any protocol at our disposal, like STAMP or SBFD, as long as it is within few milliseconds range, so we can catch failures before IGP converges. And then when the headend detects a failure, it will immediately mark the candidate path as ineligible before switching to the secondary path. Now, even after IGP converges, because the path is marked as ineligible, it will not switch back to the candidate path, which will remain unavailable for selection. And only when the failure clears and the SID list now expands exactly to the intended path we intended for it, that the path computation engine or the owner of the intent can restore the eligibility back of the candidate path 1, and now the headend can switch back to the path again. Next slide, please. This deviation, actually, sometimes it's not just due to bad news like failure, sometimes it's also due to good news like link repairs. So this is illustrated in this example. So it's the same example as before. So we have the path computation on the same network. Here we have just added a link between node B and E that at the time of computation, it was down. So the PCE would have computed the path, sent the optimized SID list as BEZ, the usual to the headend. However, now when that link repairs, we can see that the expansion of the second SID element, node E, from B, it does not go through node D anymore. It takes actually that shortcut, that new link that was repaired. And now we have the path flowing on that B to E link where we have not made bandwidth reservation and again may not be honoring our SLA or delay constraints. Next slide, please. In order to deal with this problem, we are proposing a segment resolution or a SID compaction logic that is resilient to node and or link repairs. That is, the segment list will guarantee that we come up with, will guarantee that it will always expand to the same path before or after any of these downlinks in any combination repairs. A very simple algorithm to achieve this would be to run path computation as usual on a network where the links that are down are not considered and only links with available capacity and so on are considered in order to come up with the intended path. However, in order to come up with a SID list that expresses this path, we run this algorithm on a network view where all the down links and down nodes are restored, and then we run our SID calculation. So in this case, for example, in order to express press ABDEZ with the B2E link in, we notice that we need to actually insert explicitly node D in the sedlet so that we force traffic down to D. So now when the B2E link gets repaired, it's already accounted for from a sedlist perspective. Next slide, please. So in conclusion, we're proposing a PCE and router-based solution that removes the need of having a fully specified SID list to encode the intended path of a circuit-style SR policy. And in order to deal with deviation due to failures, we introduced the concept of eligibility, which becomes an extra condition in declaring a path valid and available for selection. The router will be responsible for marking such paths ineligible upon failure detection. So we are guaranteeing the 50 millisecond switchover, and it's only the controller that has the responsibility of restoring the eligibility back, because it is the one that knows about the full intention of the path and the intended path. We also propose an algorithm that is repair resilient SID list that will deal with deviation that are due to repairs. So this concept introduced changes in various areas. Notably, it's an active candidate path selection change that takes eligibility into consideration. Any protocol communication we have between the PCE and the router. So for PISA, for example, extensions to signal that eligibility flag or concept. At the Yang model, this new property for candidate path eligibility property and the candidate path level. So we're seeking and collecting feedback from the working group, and notably seeking feedback on whether this draft shall be progressed independently or merged with the existing circuit style SR working group. Thank you.
Thank you, Amal. We have Safar on the queue. Go ahead.
Hi, Amal. Thanks. Amal, can you go to slide number 4? And while you're going there, I'm one of the authors for SR circuit style draft. And the reason that unprotected hop-by-hop agency seats were chosen, because there is 2 things to consider. One is the bandwidth reservation at all the time. So if there is a failure, we don't end up overbooking part of the network and congested, because this is for very sensitive, bandwidth sensitive traffic with absolute guarantees. So the use case is different. That's why, so that's one point. The second point is that in this picture between A and B, you have a link, and it is a protected agency SID. Then you can have a local FRR kick in. So now you have to deal with cases where your path protection is faster than local FRR, or what happens, and then you lose the control of that. So that's one issue in using the agency SID. There are 2 issues, like you end up using protected agency SIDs where FRR can kick in, and you get into this conditions where bandwidth accounting is no longer there when you are in failure mode. So
yeah, thank you, Zafar. Yeah, thank you, Zafar. So yeah, for the TLFA or any FRR in general, so the idea is to either have TLFA disabled. This is one of the prerequisites. For example, the customer who deployed this solution they did not actually want FRR in the network, or to run the connectivity check validation, for example, SBFD, at a faster rate than the TLFA. But yes, I agree that when there's TLFA, there is a risk condition where we may not detect failures. But the idea here is that we need to be able to detect failures on the head end before some other forms of repair or IGP conversions occur.
So I think both are, in my opinion, pretty bad, because in one case, you want this network to be multi-service, not only circuit style specific. So you want agency SIDs. You want routing to be using protected agencies in that network for other services that are not circuit style. So assuming that you're going to disable and make everything unprotected agency SID, I think is a very strong bad assumption. Yeah.
So
and go ahead.
Zafar, this is Himanshu. So there are 2 points. One is that in order to compress the SID list, the algorithm that we use makes sure that every link that it will transit through regular SPF, it will observe the TE, desired TE. May that be bandwidth or delay or some. So that's point one. The second point about the timers on SBFD end-to-end and the FRR timer, the hop-based FRR are changed so that for this specific SR policy, so that end-to-end protection fails first before the FRR kicks in. So you can switch over to the desired pre-built candidate path. This is how.
Yeah, that's
But
the idea. So basically, we play with the timer of the end-to-end, so we detect before any other repairs can take place.
The per hop timer is
Yeah.
little longer than the
end-to-end. SBFD or stamps. Yeah.
So basically,
Did that answer your question so far?
Not quite. We can take it offline, but that means now you're making other traffic that are relying on the TLFA of local on the link on protected agency said suffer because you want to do
they don't suffer, right? The regular FRR timers, let's say you use the FRR timers 10 millisecond, but SBFD timer for end-to-end is 3.3 milliseconds. I'm just giving you just as an example.
So let's take this offline because it looks like we're going to need to do some drawings and other things to understand the problem.
We can go over that.
Yes, that would be great.
Thank you.
Thank you so far. We have Andrew in the queue.
So thank you for the presentation. Just question and a few comments. In the document, it basically discusses dealing with new links, and the assumption is that it's going to be handled in a maintenance window in coordination with PCE. Does this imply that prior to installing a new link, somebody essentially has to go to PCE, describe where the link is going to be, what it's going to be, its characteristics, and then PCE will have to preemptively optimize the paths potentially to deal with the fact that this link is going to come up, and then only when that is complete can somebody actually plug in the wire or turn up the port?
Yeah, that is the idea. It's basically the solution here is dealing with things that are outside the human control, so like failures and repairs, but things that are within human control, like changing a TE cost or adding a new link. We think this is something that can be done during a maintenance window and with a coordination, so kind of a make before break type of workflow.
Okay, and then the other side of it is the comment on one of the first slides about BSIDs being a workaround. I'm not sure I would classify it as a workaround because to me it's just another tool in the toolbox to deal with compression just as much as a node SID is. And even in the case of dealing with the repair path, that example where you need to handle, got a down link and we need to preemptively optimize to deal with the fact that that link is going to come up, that would be the same thing as installing a new link. Even in this example, the SID list grew from 3 to 4 SIDs. So you can still find yourself in a situation where, depending on the MSD, you still might not have enough SIDs, even with compression, to have to deal with these repair solutions or to deal with new links being added.
Yes, point taken. Yeah, and when I said as a workaround, basically as a tool in the arsenal that, hey, when we get into a big SID list, what can we do? And binding SID is one of the tools that we can use in order to work around the problem of MSD, right?
Okay, and I was going to comment on the TILFA part on prefix SIDs as well, but since you stated that the assumption is that's all turned off, I'm not going to bother commenting on that.
It's not completely turned off. I said there are two solutions. So it's either some of the customer, they chose to actually turn it off, but here the idea is to run the CCV on the SR policy at a much lower interval than a TILFA. So for example, give really the SBFD, a hardware-based SBFD at 3.3 milliseconds, so it will detect failures before TILFA can react.
Gotcha. And then last kind of quick point about the eligibility. The idea of having PC control eligibility, I think, is interesting, especially if you consider the previous presentation about changing candidate path selection policy.
Exactly.
My only concern, of course, would be in a situation of a double failure. Assuming you've only got primary, secondary, you're essentially dead in the water. So if you have some kind of network flap where you end up in the double failure, you've got to wait that delay for PC to actually finally notify the head end, hey, one of these paths are now eligible. So there is that risk there, that operational risk. So it just kind of seems like, in general, it's trading binding SID complexity for other operational complexity. So thank you.
Thank you, Amal, Andrew.
Thank you.
We should definitely continue the discussion of this on the list. We're going to move on. Now we have Wei Chang, I think, or Wenwing. Who's going to do this presentation?
Hello, Charles. Can you
There we
hear
go.
me?
Yes, we can.
Oh, thank you, thank you. This is Wen Ying from China Mobile. I will present the draft SRV 6 policy resource guarantee. Next slide, please. The concept of network resource partition is introduced in TIER's IETF network slice, and NRP consists of a subset of the buffer queues scheduling resources on each of a connected set of links in the underlying network. And RFC 8986 have defined a set of well-known SOV6 endpoint behaviors, but they're not associated with the set of NRP of the link for slices or slices aggregate. So this draft defines a new SRv6 endpoint behavior which can be used to associate with a set of network resource partition. By using the end.nrp seed to build its second list, the SRv6 policy have the capability to program network resources and achieve strict SRv guarantees. Next slide, please. This page shows the changes of the draft. I have presented this draft at IETF 115 and 116 meeting. After that, the authors have made several updates. First, we improved Section 3, use cases for end.nrp behavior, update to list line as use case, and add the reference IETF Spring resource server segments. Then to better fit the command content, we changed the name of this draft to SRv6 policy resource guarantee. After that, we added Section 4, security considerations. In the latest version, we added Section 5, implementation status. Two vendors now have implemented the solution in this draft. Next slide, please. This page shows the processing of end.nrp behavior. The end.nrp behavior is a variant of the end.x behavior defined in RFC 8986. Any set instance of end.nrp behavior is associated with two sets, J1 and J2. J1 is one or more L3 adjacencies or L2 bundles. J2 is NRP of J1. When node n receives a packet destined to S and S is a local end.nrp seed, the line S15 of the end.x processing defined in RFC 8986 is replaced by the following. Submit the packet to the IPv6 module for transmission to the new destination while a member of J1 using the NRP identified by J2. Next slide, please. This is the use case for the NRP behavior. As shown in the picture 1, there are two customers with different list line requirements from P1 to P2. Customer 1's list line requires 1G bandwidth with strict SLA guarantee, and customer 2 requires 2G bandwidth. As shown in the table, for PE1 node, end.nrp seed 11 is associated with Q1 on port G100 and indicates to forward traffic to neighbor P1 via this NRP. And end.nrp state 21 is associated with Q2 on the same port and indicates to forward traffic to neighbor P1 via this NRP. Then the control can use the end.nrp state to build the explicit path for the SRv6 policy. In this use case, customer one's list line is SRv6 policy 1 with explicit path end.nrp 11, 12, and 13. Customer 2's explicit path is end.nrp 21, 22, and 23. In this way, the traffic of customer 1 and the customer 2 will be forwarded to P2 through the NRPs that are preserved for each hop link on the paths of SRv6 policy 1 and SRv6 policy 2, respectively, so that to provide strict end-to-end resource guarantee. Next slide, please. The SRv6 end.nrp function magazine have been implemented by ZTE and H3C, and ChinaMobile has completed the basic verification. Next slide, please. This page shows the discussion email list. Previously, the main issue discussed about this draft was the difference with draft resource-aware segments. Recently, the mailing list has reached a consensus. Draft resource-aware segments is a very useful framework document, but it does not define any specific solution. It provides common architectural ground for development of such solution. In addition, we need the specific solution. So this draft proposed specific solutions. It defines the specific behavior and NRP behavior and actual application scenarios. This draft can provide guidance when deploying. The mail list discussion are shown as the following. Next slide, please. Any comments are welcome. And let me add some information. On September 28 of last year, the authors submit a request for work group adoption, and the chair has added it to the list. This is the link. Now that all the issues discussed on the mail list has been resolved, we would like to request for work group adoption again. That's all. Thank you, everyone. Thank you.
Thanks for the presentation. We have several people in the queue. Ketan, go ahead.
Ketan Talaulikar, Cisco. Thanks for the presentation and sharing the updates. The basic, I think, premise still remains that we need at every hop or along the path this large number of SIDs, one per NRP. I think this has been discussed previously, but I would like to ask whether the authors have considered using an indication in the packet rather than instantiating SIDs for every NRP in this manner. So basically, the NRP indication is carried in the data packet itself.
The NRP it's previously result for array hop of the link of the SRv6 explicit path.
Okay. Okay. I'll just maybe summarize that there are proposals out there. One of them is a working group draft in spring in 6-man that talks about conveying NRP in the packet itself. That does eliminates the need for having a per NRP SID instantiated in the network.
Jim, go ahead.
Yeah, Jim Guichard, Futureway. I'm speaking without my AD hat on, kind of. I'm a little bit concerned about this document because we already have the resource-aware segment document as a working group document. And you made a comment previously that that document doesn't provide any solution, which is actually inaccurate, because if you read that document, it basically says that you can allocate multiple index SIDs on the device to indicate which particular slice this belongs to. So there is a solution actually in that document. So I certainly would encourage you to, if that conversation hasn't already happened, to talk to the authors of the already existing working group document. Because what I don't want to see, and this is where the AD hat comes back on again, is multiple documents being adopted into the working group that are basically trying to do the same thing. I'd rather see a document that fully fleshes out everything and to avoid the confusion. So really just a pointer, let's have that conversation with the existing working group document and see where, if this is necessary or not.
Thanks, Jim. We're going to move on to Srihari.
Yeah, Srihari Sangle from Juniper. I had a similar comment what Ketan said. I would encourage the authors to look at from a scalability perspective as to how many said end behaviors you're going to be creating in the network, and this seems very similar to what network slicing problems and the solution that the TEAS working group has solved. So you may want to look at what slicing concepts can be derived for solving the similar problem.
Okay, thank you. Ryan.
Hi, I'm Zan. Reply to Curtin. We have considered the NRPID encapsulated in the date, but we think in the scalability, in TEAS scalability draft, it has defined two solutions. That is NRP-based, NRP-based solution mechanism and resource seed. So we think so. That's the answer. And to Jim, yes, we think this resource working group is the architecture. It doesn't define the solutions. So yeah.
So, sorry, Jim is talking. So we're going to take this to the list. So what Jim's point is that there's already a draft that potentially shows a solution. And maybe if we need to move this further, we either combine, merge, select one, something along those lines. So we need to take the discussion to the list as we talk about potential adoption and what the paths of that look like. Okay. So the guidance that we're getting from Jim is, of course, that it looks better if we have one draft than with potentially multiple things in it, than multiple drafts, each defining one piece of the puzzle. So let's take that to the list.
Thank you.
And let's move forward. As I mentioned at the very beginning, yes, we know there's a queue of adoption and working list calls that we're going to work harder on getting through. We're going to move on to Luigi, who's going to talk about proof of transit.
Thank you.
Hi. I actually asked the control of the slides. But these are not my slides. We can fall back to
right. Bruno has the
interrupt
slides.
to Bruno. Next.
Your request for the slide, I'll grant you the right, but I can come back to sharing the slide.
So you will share?
Yes, maybe I need to deny you the right back.
So I create an issue?
No, sorry.
Yes.
Is to make sure that Bruno is awake.
No, 2 seconds. Okay, that okay?
Yes, next. So Luigi, what is the draft is about, the draft we submitted and we shared on the mailing list is about the problem of pass verification, okay? How to prove that the packet in a certain way goes exactly through at least a set of nodes that we want that the packet traffic goes through, because there is a difference between what we want and what actually happens on the data plane. So this is a big issue in the sense that we can have several use cases. One of the first documents that was tackling this problem is actually drafting the SFC working group, was about exactly proof of transit, and it never ended up published as an RFC. Okay, now we are interested not specifically in SFC, but in the context of SRv6 to make sure that the traffic that we are setting up follows exactly the list that we have in the SRH header. Okay. Greg, you want to ask right away?
Thank you, Greg Mirsky, Ericsson, and thank you for recognizing the work on proof of transit and SFC as part of in situ OAM. So proof of transit is one of the modes, trace options in IAM. And my understanding, it's not SFC specific. It's just any node that has shared Shamir secret can do that. So I would really ask, why would not take this approach that's been discussed and quite advanced. So the discussion that happened and the work that's been put in with the SSS approach allowed for scale and security. So a lot of questions, and I would really encourage looking at this approach and continue on with it.
Thank you. So the reason why is because our requirements were to have something lightweight and efficient. So as you will see, this solution is simpler in a certain way compared to that proposal, and doesn't cover everything because, for example, we are not able to identify where something happened. So we just and the egress, we can say this went through the right path, this one didn't. So it's just because we use a simpler approach based on symmetric cryptography that works quite well, actually. We have good performance. That's the only reason. There was no other reason, to be honest.
Okay. Okay, that's fair, and I understand offers perspective, but might be just adding some information about why this preferred compared to will be beneficial. Thank you.
Point well taken. Actually, Joel sent us also an email with exactly the same point, and we will do it. Thanks.
Hi, Jeff Haas. Sorry, I haven't actually read the draft in question, and I have not followed this stuff on the list, but I've had a number of conversations with Peter on this specific set of technologies. So I'll be echoing some things that we've discussed for the room. One of the big things that has come up in part of our conversations is, sure, you can prove with these types of technologies that something has touched an individual node. Well, that's what you can prove with these types of techs. What has been difficult to discover in our discussions is why that's helpful in a lot of circumstances. The biggest portion of our discussion is a lot of the places that this is somewhat useful is in many cases you're really trying to say, did some node that you don't want to touch it, has that actually been involved in the picture? You can't prove that with these types of technologies. So what's the actual motivation that proving that a specific node has touched a thing, especially when the problem statement, as best I understand it, doesn't prove that a piece of work has happened. Now, as an example, in service function chaining, if node 3 in a 5-node chain doesn't actually do its work, you can't actually prove that.
Absolutely right. So thank you for taking the mic. I was planning to conclude this slide stating that what I'm presenting is something specific solution for a specific context. The problem is much bigger, and the ones you just mentioned is very, very hard. Okay, and there is a side meeting this evening which will discuss this bigger issue. And for all the people interested, go there. I'll be there as well. I will not present, but there are interesting discussion going over there. So thank you, Jeff. So next. In the 4 minutes left, I will explain what we do. So it's really, really specific to Service 6. What we do is basically we take the HMAC at the ingress. We calculate the HMAC as defined in RFC 8754. And then we use a series of pre-shared symmetric key to recursively encrypt this HMAC. Okay, so it's like an onion. We built layers of encryption at the ingress. Okay, and then along the path, each segment has to take out one layer. So basically, the encryption is done in a LIFO policy. Basically, the last key to be used for the last layer of encryption at the ingress is actually then used at the first segment to take out, so decrypt one layer. Okay, so the ingress has to share a set of keys with all the segments, but the segments, the node along the path, they just need one key. Okay, except for the egress at the end, because we have to verify the HMAC. Okay, so at the ingress is just calculate the HMAC, encrypt recursively. Next. So as I said, then along the path, they encrypt, we don't verify anything. Okay, we use the pre-shared key in order to decrypt. Next. So on the egress, we do one last time the same operation of decryption. And then what we do is we use the pre-shared secret in order to recompute HMAC. And if what we obtain from the SRH header is equal what we found in the TLV we proposed that was sent along the path, then we are done. Okay, if something went wrong, okay, it doesn't match, means that somebody either used the wrong key or the packet didn't go through the set of nodes that it was supposed to go through, or in a different order, just didn't go how it was supposed to go. Next. I will skip this in the interest of time. Next. So the idea as a first proposal is just to enlarge a little bit the HMAC TLV. So basically, it will be a new TLV, but we have the key set ID, which is just an identification that allows us to retrieve the right key to be used for the crypto operation. Unknowns, so to add some salt so that we don't have each and every time the same TLV value in the encryption Okay, otherwise this is open to attacks. And then we have what is the encrypted edge mark, so what we recursively encrypt. Now, the nice idea is, the thing is that with this set of operation, at the end of the, let's say, SRv6 tunnel, we are able to say it went through this list of segments or not. What we lose with this approach is that we cannot verify the H marker on each and every segment. Why? Because it's encrypted. And along the path, we don't have all the keys. Okay? Next. So we implemented this in the Linux kernel, then we did all the work, including CLI operation and everything that goes inside the kernel. Next. What is the interesting part insofar is that in the first evaluation and in the scenario that we use, actually the performance are good in the sense that either when you compare HMAC calculated at each and every segment and what we propose here, at the end of the day has the same cost in terms of delay. Okay, and I can show you a demo offline if anybody is interested. So these are just initial results, but in my opinion, promising. And that's it. None?
Hello. Thanks for presentation. Nangang from Huawei Technology. Just one question. Can the solution be applied for preventing malicious path deviation? I mean, malicious path modification.
I would reply, it depends. So between the segments, I mean, if you run this as an overlay, in the middle you can have detour and you cannot detect them. You just can detect whether the packet went through the set of nodes, not between the nodes. This you cannot detect. But you can detect anything that goes around the nodes. It does not go through those kinds of nodes. So,
okay, because I was just thinking about what will happen if the middle routers remove the option or
what we do is just we drop the packet at the egress, so not in the middle, because the verification is at the end of the segment list. So when it goes out, you verify, doesn't match the verification, you drop the packet. But if you skip a router in the middle, the other will do the decryption operation, but they cannot verify. So the packet will be forwarded until
so we need to do checking at every egress router, right?
Yeah, at the egress router.
Okay,
yeah,
thanks.
Exactly.
Hey, Luigi. A quick question. Jim Guichard from FutureWay, no AD hat on. Is this in any way related to the NASR side meeting? And if it is, could you say a couple of words
that
about
was the same
so
meeting I was mentioning.
Yeah,
to
so
be
people in
honest,
the
we
room-
started this at the beginning of 2023, and then Nasser came along, and so obviously we discussed together because it's strongly overlapping. But
the only reason I mention it is because if people in the room are interested in this subject, then there is a side meeting on NASR.
Yeah, I was
that,
mentioning again Jeff's comment, because Nasser is bigger, it's more general problem. This is it's a nice solution, but very specific, I would say.
Okay, thank you.
Robin, are you running to the mic? Go ahead, and then we're going to move on to the next one.
Robin from Huawei, quickly a question. So that's if this path validation is added, how much overhead will be added for the SRv6 packet header?
So for the Linux kernel, the implementation that we have with the AES as a crypto algorithm, in terms of delay, is less than 1 millisecond in a setup with 36 milliseconds round trip time. So basically, the cost is negligible. What you lose if you do a file transfer it takes a little bit longer because the TLV is slightly bigger. So obviously you are wasting a little bit of bandwidth. But again, is on a 1 gigabyte transfer, which in the setup we did is 15 minutes because we throttled the bandwidth. It's a few seconds compared to on a transfer that takes more than 10 minutes. So I mean, you lose something, but not that much.
Okay.
Thank you, Luigi. So we're going to move on to the last scheduled presentation for today. Jun Liu, path verification for based on SRv6. We still have about 15 minutes left, and we scheduled this for 10 minutes. But this is going to be the last session, or the last presentation. This room is going to be used over lunch for the working group chairs meeting, which means that people need to set up, and so we need to get out at 11:30. So this is going to be the last presentation. Thanks. Junlu, are you there?
Yeah. Can you hear me, Chair?
Yes, we can.
Okay, thanks. Hello, guys. I'm Jun from Tsinghua University. Today I will talk about the draft about the path verification solutions based on SRv6. As just Bruno said, we know, or we all know that the path verification are the most important work to guarantee the network safeties. And the emergence of SRv6 brings the opportunities to make the network path trusted by using a lightweight IP headers. So next page. The content of this work as follows. The first one, we talk about what is the path verification for and why we use the path verification. And the second one, we introduce the existing works and our SRTPP. And then we introduce our prototypes about SRTPP. We can see the implementations process of this method. So next page, please. So the statement of our draft is as follows. When we use the SRTPP, we want to fix the problems in the packet tampering and the source spoofing. We also use them. We use it to fix the problem of the path deviations with 3 ways. That can then just set maybe the router hard path, router additions, and other forwardings. Also, we fix the problem of denied service, and we think the privacy link is also a very important topics. So next page. Okay, in a word, when we talk about the path verification, we make sure that the path is trusted, authorized, and not to be traversed. So the existing works are divided into 2 ways. The varying the planned passes, also we know that do the things right, and verifying the traversed paths, we also count that do the right things. So the first one, the works such as Sling and OPT often take in control plans and only make sure the packets are dropped when verifying the faults. That answered your next question. They not mentioned how to locate the faults. And the second one is just like PPV and RFL, and they often did in the data plans verify the traversed path and only enable the destinations node to locate the faults and cost with the link resources. So now we focus on the new challenges, ensure the integrities of the original path is not destroyed when the natural flow is rewarded by the entrusted node, and how to make the cost acceptable and to protect the path information at the same time. Next page, please. Here are the terminologies about our draft, and we noted that the SID and SL and AR, also called the P router, in the draft defined by ourselves. So it is not different. It is different from the original ones in the SRH. Next page. So this draft described a trust network path verification based on SR6, supporting the network path verifications with the path information protections. So here are the 3 specific functional goals, just as the source and path verifications, the privacy protections, and fault localizations. Okay, next page. Okay, just to mention one note that the SRTPP provides distributed path verifications using distributed SR routers, and the centralized based the fault location use the centralized SR controllers. Okay. So let's move on the details about our SRTPP. The first step is to initialize the path and the package. We can see the path initialization process shown in the right figures. In this step, we use the local keys of HB routers and the path creating time to generate the session keys using the hash functions with the session steps, and to notify the senders of the session keys and IP address about the interpath. And also the package is initialized in this step. Okay, next step. And the second step is the verification. The verification process is divided into 4 parts. The path initiation, key generations, the upstream verifications to obtain the downstream IP address, and judge if the IP address is in leak. If the answer is yes, we just update the SRD, and if the answer is no, we just drop the packet, and then we replace the headers of the downstream routers. Okay, next page. And also in SRTPP, we focus on the fault localizations, which may be caused by the payload alterations by the upstream routers and the malicious directions by other routers. When the fault occurs, the routers will notify the controller to judge where the error occurs. And with SRTPP, we see that we can face a problem about maybe the packet alterations, the path deviations, the DDoS, and we also protect the privacy. Okay, next page. Okay, so how to implement TPP? We move on to the core use case. We just use the Dell TrapES servers as the SR controllers, senders, the P routers, and the receivers. And in each part, we have some functions on the servers. So we just did the element exam, and we got some result, but we will continue to work on it. Okay. So, okay, next page. Here are some normative references, and okay, that's all for my presentation. Thank you.
Thank you. Anyone have any questions, comments? Antoine, go ahead.
Hello, I have a question regarding the claim that you make that SRTPP is protecting privacy. What is the threat model that you adopt for this privacy protection? Because from the best of my understanding of reading both the draft and the academic research article that you published a few years ago, you don't re-encrypt the packet with every segment, and I think that in this way, the packet payload can be used to de-anonymize the traffic. So, what is my question was, what is the threat model for the privacy protection that you want to provide with SRTPP?
Okay, thanks for your question. As a pre-router didn't have the all paths of the route, they did not know the destination, the senders. Take the if there are any faults during the verification, for just as the payload alterations about the upstream routers, the routers cannot parse SID and got nested IP address correctly, which may be caused by the wrong upstream router IP address or the wrong timestamps. We just dropped the packet. So the P routers they didn't know the sender and the destination.
But for instance, if you are an attacker and you can wiretap several links, and you can monitor the payload of packets, and you see two packets with similar payload on the path, then you can correlate those packets together maybe. So my question was whether by only passive observation and not active detecting active alteration, whether you would protect against an attacker that is able to wiretap in two separate links. For instance, if he controls two areas where close to the source and close to the destination, for instance.
Sorry, I just didn't got the last part.
So I wanted to know how you would suggest protecting against an attacker that controls links that are close to the source, close to the destination, and without changing the packet payload. The payload can be used as a marker for the packet and to correlate source and destination.
Yes, I think it is. I think it's a good idea to just use maybe the payload for the different two senders.
Okay.
Okay.
So maybe I can send more detailed information about that on the mailing list or offline, and we can discuss this point.
Yes, thank you.
Thank you for the presentation. So with this, we're done. Thank you for coming to Spring this morning. Again, just a reminder, there's that SRv6 Ops BOF on Friday morning, which I think should be of interest to everyone here. And we'll see you in Vancouver. Thank you. Yes, we'll see you next time.
See you next time.
Number one, I think the chair, for the compression.